Hey everyone, I'm Ren, and this is episode 10 again of Farm and G's Robot Livestream. Last week we had some technical difficulties, so we're going to try and get you some better resolution so you can see what we're actually doing. I'm here at the farm in Watsonville, California with our Amigas and with our engineers, Kyle and Edgar. They're going to guide us through integrating an Xbox controller with the Amiga and also adding CAN devices to our CAN bus. Take it away, Kyle or Edgar.
Hey, what's going on, everyone? Kyle here. I'm one of the Farm and G engineers, robotic software, computer vision. I am in New York right now.
Hello, everyone. I'm Edgar. I'm based in Barcelona. I'm also one of computer vision and robotics engineer, Farm and G. So yeah, ready.
Yeah. So I think the first half hour or so of this stream, what we'll do is we'll kick off with kind of going through using the CAN bus service. So in order to control the Amiga and drive it around, the CAN bus service is the interface that you'll use. And rather than continuing to go through our tutorials, where we've done the introduction tutorial and then the camera streamer to set up an app and then stream video, the next step would be the virtual joystick tutorial, which actually interacts with the CAN bus. It reads streams from it, as well as sends commands to the CAN bus to drive the Amiga. We thought we'd kind of pivot and do a custom example instead of just walking through the tutorials more, in order to show this new little custom utility Edgar just whipped up in order to drive the robot around with an Xbox controller.
Cool.
So yeah, I think first step will be kind of talking through the CAN bus service and how to interact. Edgar is sharing his screen, so maybe I'll just point him a little bit. If you could bring up the Farm and G Amiga repository on GitHub. So the Farm and G Amiga is kind of the higher level API for interacting with the different devices and services that we provide. The two places that you'll want to look, and maybe we can do this side by side. One is in protos, which are our proto-defined messages that we use for that the service either sends or receives, and we create a client of that service in order to listen or command. So we have custom defined CAN bus proto messages that you use, as well as the RPC streams are defined here. I guess quick reminder about going through the gRPC overview that we mentioned in the introductory tutorial that kind of talks about the different types of RPC streams. There's server streaming, where the client will send a request and the server will respond back with a bunch of messages. So that's how the camera stream works. Is the camera client that you make in your app will send a request to the camera service, and the camera service will send back a stream of images. And then there's also, well, there's four types. There's the server streaming, there's client streaming, which is the opposite direction. There's bidirectional streaming, which is what the CAN bus control actually is, where for every message the client sends, the service sends one back. And then there's unary streaming, which is just a one-to-one, which we don't use too often, just for things like camera calibration and stuff like that. And then to the other side is the Python implementation of the CAN bus client, which is what Edgar has pulled up here. So I think looking at both of these is pretty useful. And I'm just watching on the YouTube, and it's not super clear still. Could be on my side. Okay, cool. Yeah, we'll make sure that the quality is decent enough so that you can read and actually see what we're doing on this retake, re-record. Yeah. Okay. So with the CAN bus service, up top at the top of the proto file on the left, you'll see we define the RPC, the procedures in order for communicating between the CAN bus service, which is running on your brain by default, If you want to turn it off or turn it back on, reset it, things like that, that's on the settings page of your brain. So the idea is that the service is always running, and then you create a client that can connect to that. So if you use the Recorder app, you'll create Oak camera clients that'll connect to the Oak services, as well as a Canvas service. In this case, with this joystick control, since we're not streaming any images, all we're doing is creating a Canvas client and connecting to the Canvas service. So there's these different RPC calls, which are ways to connect to the service. So for instance, the first one up top on line 21 is the stream Canvas messages call, where you'll send a single stream Canvas request from your client to the Canvas service, and the Canvas service will return a stream of stream Canvas replies. The stream Canvas request is just an empty message right now. And the stream, just to initiate the stream from the service, and then the stream Canvas reply is going to be, there's sort of like a nested level of these proto-defined message packets, but basically you'll have a repeated or like an iterable container of raw Canvas messages. In the stream Canvas reply. So line one, what is it? 106, you'll see there's the repeated raw Canvas message, and the raw Canvas messages, that's what's coming back in the reply. And then each one has that raw Canvas message, which will have a timestamp in the form of a double right now. That's the time that it was received by the brain on the CAN socket. It'll have an ID, which is the node ID of the Canvas, of the Canvas message. So quick detail on that. Every device on the Canvas has a node ID, and that's kind of like a unique identifier of that device. So for instance, the pendant has the node ID in hex. It would be 0 cross F, or so F, so that would be what, 15? And the brain would have the node ID of E, or sorry, the dashboard has the node ID of E, and so that would be 14 in decimal values. And then the 4 motors, for instance, are A, B, C, and D. That's 10, 11, 12, and 13. And then for different message type, there's different protocol ranges. We kind of fall loosely into the CAN open protocol. So for instance, like TPD01s and RPD01s, those are requests and responses. So you'd send an RPD01 request on like the 200 range, and you get a TPD01 response back on the 180 range. So the node ID is that value. It's the or the ID field in the raw Canvas message is the node ID of the device and the message range you want to send it in. So if you wanted to send on the range 180 with node ID E, you would send 18E, and these are all hex values. The error in the remote transmission, you can kind of ignore those fields unless you're an advanced user. And then the data, that's going to be an 8-byte packet. Typically 8-byte, it doesn't have to be. It can be anywhere from 0 to 8, but usually an up to 8-byte packet of data that needs to be decoded in order to understand what values are present. So yeah, sorry. And then if we can go back up to the RPC calls, Edgar. For some of these RPC calls, we have a convenience function in the Canvas client. So for instance, if you want to call the stream Canvas messages RPC, which is line 21 in the proto file, that corresponds to the stream raw call on line 40. So that you can just do, if you've line 40 of the Canvas client on the right, if you've created a Canvas client, then you can just do, my Canvas client dot stream raw, and that'll handle the RPC definitions for you. We have the same thing for streaming motor states, which will respond with a stream of motor voltage, amperage, temperature, and RPM, as well as the like ASI encoding of the state of the motor. So for those two, we have this utility function that you can just use. For some of them, we haven't created that utility function. So for instance, for the streaming the twist states, you'll use the proto, you'll actually create a service stub, and you'll make that, or the client will have a service stub and you'll actually do the call yourself. So you would do like self.myClient, myCanvasClient.stub, .stream, vehicle twist state. And for these, we have examples in the FarmNG Amiga repository, FarmNG Amiga Pi examples, and you can see some of them there.
Yeah, maybe Kyle, you want to clarify like the difference between using the raw canvas messages and then this new twist API?
Yeah, yeah. So we've added this new twist API. The idea is it's a little bit closer to both. For one, it directly correlates to the ROS bridge. So we have a ROS bridge out. If you want to control the Amiga using a ROS node instead of gRPC, you can use this ROS bridge. We have a live stream about that already out. And then those messages are a direct parallel to the ROS twist message, which is in the geometry messages package. But we also have our own utility for if you want to just control with this twist message instead of interacting with the raw canvas messages. It might be a little bit higher level of an API, so a little more approachable and easier to interact with, where you just send the command of a linear x velocity. So that's the forward direction, or forward or back. Back would be negative. And then an angular velocity with left being positive and right being negative in radians per second. The linear velocities in meters per second. And right now, the linear velocity y would be sideways, which with the current skid steer model of the Amiga, that's always going to be 0. You're not going to try to command the robot to drive to the side yet. Yeah, so you can set up the twist stream. Edgar, do you want to show the example for that?
Yeah, it's in FarmNG Pi examples. Vehicle twist.
So this might be an easier interaction to use, where you'll just set up sending and receiving twist messages. There's no canvas message parsing. That's all done behind the scenes for you by the Canvas service. And you'll see here in line 35 of the example on the right, there's that stream equals client.stub.send vehicle twist command. That's the RPC call in order to start the stream of twist messages. Yeah, so that's definitely the recommended if you just want to go, just straight simple control of the Amiga. If you do want to stream the raw messages, the virtual joystick example uses the raw canvas message streaming and goes through kind of parsing those. So that's a good example if you want to get a little more in detail. And maybe we can just show the packet.py file as well, Edgar.
Yeah, so that one is here, canvas, packet.
So this shows a little bit more of the some of the raw interaction with the Canvas messages after decoding. So you'll see there the dashboard independent node IDs 0E and 0F. Like I was mentioning, those are hex values. The Amiga control state is just an enumerator of the different states of the Amiga that corresponds to the dashboard control states. We have a graph on the website. In the amiga.farmng.com website that probably in the Amiga overview, Amiga control states page, the second one. So this shows the different states the Amiga can be in and the transitions for them as it currently stands. And then there's a few, specific things for other for classes, but this packet class in line 66 on the right is a base class for CAN packets that is inherited by other packets. So you'll see that the Amiga RPD01 and the Amiga TPD01 packets inherit that base class of packet. And yeah, the Amiga RPD01 is the request message for control of the Amiga. So if you go to your dashboard, you go to the auto tab, which is the third tab, the A with the circle, and you click enable auto or auto ready, it'll kick into auto ready state as long as it's not e-stopped. And then it'll be listening for these Amiga RPD01 messages where if you set the state to be auto active and then you send a command velocity and a command angular rate, the Amiga will follow that as long as it is a safe command that you're sending. And so, yeah, so to control the Amiga, you would send these. If you're using the twist API, your twist messages, the linear and angular velocity will be translated to an Amiga RPD01 packet and then encoded and sent out on the CAN bus through the brain. And then the dashboard will reply with a stream of Amiga TPD01 messages, which would be slightly lower, which is a very similar packet. But this is the measured values by the dashboard. And the dashboard actually streams these Amiga TPD01 messages by default, even if you're not sending RPD01 messages. And yeah, maybe Edgar, if you can zoom in just a little on the web browsers, it might make it a little clearer to people. And one note about the Amiga TPD01 and RPD01 messages: in firmware version v0.1.9 and FarmNG Amiga version v007, we added auto control of PTO, which is our rotary actuators. So if you have like a compost spreader or I don't know, some sort of like tilling device that's rotating, that's controlled by a PTO, and you can control that automatically now, as well as H-bridge control, which is a linear actuator. So if you have like a plow or something that you're raising and lowering, you can now control those with the Amiga RPD01 and TPD01 messages. When you do upgrade one, you should upgrade both. So if you upgrade the brain to version 0.1.2 or version 1.2.2, that'll come with FarmNG Amiga v009, but anything after v007, you'll want to match your firmware to v019. And likewise, if you decide to upgrade your dashboard to v019, you should upgrade your brain to the latest software, just so that they're both using the 8-byte packet, which has the auto H-bridge and auto PTO control. Yeah, anything that I've missed, Edgar, before we dive into the joystick or the controller example?
I think that it's fine. Yeah.
Cool. Yeah, so I would just recommend to check out the virtual joystick tutorial. There's a page on how to interact with the CAN bus and look at the Python code there. And then we have some other examples as well that are interacting with the CAN bus service in the FarmNG Amiga package. So those are good resources to look through.
Yes, here examples. You mean this one, right?
Well, this one is if you have if you've recorded a log with the recorder app on your brain and you want to play it back and see the CAN messages. So that is one that's not actually using the CAN bus client though, right? That would just be playing back the log file. Whereas the motor state stream and the vehicle twist would both be using the CAN bus client and creating a stream. And then the virtual joystick, which is its own repository.
Okay. Yeah. Sounds good. Nice. Okay. So do you think we can jump to the example? Okay.
Yeah. Let's pivot and let's show how you can use this to create a something custom.
Nice. Good. Let me go first here. So what we're going to do now is basically to implement the Canvas client using a standard Xbox controller. It's here. So it's an Xbox controller that I got from Amazon. So,
and Edgar, can you zoom in a little on the VS Code as well while you're Control-Shift+ should do it.
now it's a bit better.
Yeah, I think that's a bit better.
Okay. I will be yeah, so basically the repository that contains this implementation, it's Amiga Xbox controller. It's under FarmNG Amiga organization. And so let me go first through the README. So here I wrote some instructions about how to start using or implementing this example. Some things you need. First of all, it's the Amiga, the FarmNG Amiga Intelligence Kit. See now there is a typo here. We'll fix later. So that's basically the Amiga that includes the brain. Yeah, that's why we're going to implement this canvas controller with the brain. And then, as I said now, the Xbox wireless controller. So in my case, I bought just a standard Xbox controller. Just make sure that this controller has the USB stick so that you can connect. Here it's this small stick that I'm going to explain now. Also, a small configuration you need to do on that. But yeah, it should be pretty easy to get one of these for you. So the main idea, there are two different ways to implement this controller. The first one is plugging this stick to your computer. That's the one we're going to show here. You stick the USB in your computer, and then what we're going to do is just send commands with the Xbox controller that will go to your computer, and then through the Canvas gRPC client, we're going to send the actual commands to the Amiga. That's the case number one. Case number two, that maybe we can do it another time, it's to plug the USB right in the brain. That could be another option. That also might take some time to install all the drivers. So now for simplicity, we're going to through the first case. And also the reason we wanted to show that is that we are very interested in showing how to remote control the Amiga. And with this example, through the gRPC Canvas client, means that from my computer, I'm based in Barcelona, I'm gonna drive through the internet with this gRPC client at the Amiga where Gren is located in California, United States. So we're gonna drive the Amiga overseas. That's with this small example. It's kind of exciting. So that's kind of the big picture of what we're going to do with an Amiga wireless Xbox wireless controller. So now let's get to the kind of details in terms more software. What do you need? So first of all, you will need to install this system dependency, the USB. This is kind of the driver for the stick to pair the connection between the controller and your computer. And we are going to use this XO package. So that's basically the actual driver for the wireless dongle, this small USB we are referring this time. So what I suggest is you go through the instructions here. I found this kind of easy to follow, so I hope that you can install easily without problems. So they have, I think, somewhere here, installation. They have a very short guide. It's very simple. You need to just git clone this repository in your laptop. And then with these few commands, you just install the driver for the USB stick. So in order to validate that, something kind of useful that I found is that so once you have the driver, you will have to pair the your controller with the stick. So the controller, it has here where the Xbox logo, it's like a small button that you need to press. So in order to pair, if everything went correctly, no issues with the drivers. So you will see that when you plug the USB, it has also a small button that will start blinking a small white light, and the same here. So in order to pair, you will have to press both buttons. You will see that they will blink for in less than a second, and if you manage to pair correctly, you will see that both lights will become stable. That's where you see that the controller and the USB, they are paired, and you're ready to start to use it. So that's a kind of a first step to do: install the driver, pair the controller and the USB stick with your computer. That's
just
yeah.
a quick comment. This is all supported for Linux installation and running. We know that the gRPC code and the FarmNG Amiga package can run on Mac and Windows with WSL. So yeah, if you want to try and run this on a Mac or on a Windows running WSL, I'd say there's probably information out there on connecting the controller. If you're having trouble with it or anything like that, let us know in the comments. Let us know on Discord so we can try to help you out and kind of get some instructions for those as well. But for now, we just have the Linux instructions, and we'll probably leave it there unless somebody specifically asks for Mac or Windows.
Yeah, good point, Kyle. Yeah, thank you. Clarify that. Cool. So yeah, so this was kind of the installation steps that you need to do before that. And then what I'm going to do now is go through the code. I'm going to explain. You will see that it's kind of a short script, what I needed to implement. And yeah, so let's go through the code. Yeah, just to give more context, so the repository is very small. Here you have some files for the repository to make it kind of follow the standard practices, but the main code is here in main.py. So now I'm gonna switch to VS Code because it's the same thing. So I hope you see clearly. Yeah, so this main.py, I implemented kind of following to make it simple in a couple of classes. So the first one is this Xbox controller. Then we have this Amiga Xbox controller client, which is the one implementing the client. And then you will see from here, I like to start from bottom, where you usually implement the main method to start your programs, these kind of simple scripts. So, and also as a reminder, if you have been following us, we make use very often, well, actually the whole FarmNG Amiga library is implemented in terms of, well, gRPC, but also in terms of async IO, which is the standard library for Python to create kind of applications with concurrent processes. So you will see here that this is kind of a pattern that we found out that work for our application. So usually you create this, you get the loop, the active loop from async IO, and then you will have this implement this method, run until complete, to start running this client, the Amiga Xbox controller client declared here. You will also notice probably by the end of the tutorial that how we are going to implement these arguments that we have here, host and port, which are used to create the Canvas client that Kyle was describing before. So you can tune these parameters. You will see how later to run it, well, to basically connect or locally or just by passing the IP to connect over the network. So let's go first to this class, call it Amiga Xbox Controller Client, which is defined here. And this class will have basically the other class, Xbox Controller, and then also the Canvas client. So here is where we implement the Canvas client that Kyle explained before from FarmNG Amiga. The way you import the client, it's FarmNG. So the FarmNG Amiga, it's like a library with different modules where you can find the Oak, Canvas, and others. And the way to import it is through FarmNG Canvas, Canvas client, then you import the Canvas client. From here, it's where you create it using the configuration you want based on the address and port. And before going to the controller, just let me show here the way, basically how you, so in order to implement this example, we are using mainly the interface that the RPC that Kyle explained before, send vehicle twist command. So this is basically a bidirectional RPC, which means that you are streaming at the same time, sending commands and receiving like the state of the Amiga. This is kind of an extension of the example we showed before to stream I think it's called a twist example, right? So this is a small extension of that example. So you can see here we have the Canvas client, stop, and then we call the RPC method, and then we pass this generator. So this generator, it's a function that it's part of the Amiga Xbox controller client that basically has a forever loop that will yield sending the send vehicle twist command request. And the important part is this line, which is basically, so imagine this as kind of a two processes thing. When we call this run method, which is the starting point of our controller, basically we are creating the stream, and we have this for loop that basically will start sending messages, but in kind of a separated thread. We have the generator that has also a for loop that it's basically iterating. And here, that's the important line because in order to get the values to send to the Amiga, we implemented this auxiliary class called Amiga Xbox Controller that will have an internal queue basically monitoring the signals we get every time we press a button or we move the joystick from the controller. And every time that we implement the signal, so it will put in a queue, and then from this main method, we'll get that value from the queue and send it over the RPC method. That's kind of the way it works. It can be a bit messy, but I suggest, yeah, to kind of play it around a bit. That's why it's also interesting to try this the twist example we have, because yeah, you will see that you can easily implement the bidirectional following this pattern. So last that I want to show is the Xbox controller. So something that I forgot to mention before is that in order to easily implement in Python the Xbox controller, we're going to use a library called Pygame. So Pygame, the reason why we're using Pygame is that they provide for us, I'm going to show it here, this joystick API, which makes our life easier in this case, because as soon as you have your Xbox controller paired with the USB stick in your computer, then with this joystick API, you directly get access to all the signals from the controller in standard Python. Yeah, this helped me a lot to implement these examples. So I recommend also checking out Pygame. There are other utilities that you can use. Okay, so some other things about this Xbox controller. As I said, we're going to use a queue that basically it's mechanism that we'll use to share the data from the actual controller and the main thread where we implement the RPC method. In order to do that, we are also going to use the multiprocessing library from Python. This is also one of the standard Python libraries to work with multiprocesses, subprocesses. And this library, it has, well, in this example, we are going to use the process and queue classes. The queue, as we said, it's going to be the data structure so that we can share the data between the subprocess and the main process. And then process is basically the actual process. So here we are going to, it's where we are going to implement Pygame, which is another background process that basically will read from the joystick. And the way to implement it in the multiprocessing library, and when you want to create a process, you need to create an instance of the process class. You pass the main method that you want to run in the background. I call it here loop Pygame. And then you can also pass some arguments. Here, I just decided to pass the device ID, defining, in that case, the Xbox controller. And the other argument I pass here is the queue that we are going to use later to extract the values that we read from the controller.
And I'll just shout out Edgar's use of the queue. I think this is, as you mentioned, it's a good way to share information between a main process and a sub-process or multiple sub-processes. Here he used the multi-processing implementation of queue. Async IO also has a queue implementation. And I think it's you'll probably see it throughout our code base, and it's something we would recommend you adopt or at least start to kind of look into, because I think it could help your programming.
I didn't explore here to use the async IO queue, but yeah, I think it's definitely possible. I think it's a bit more complicated when you have when you use the multiprocessing to share the data with async IO queues. I think that you need to do some tricks. I know even that there are some libraries that are abstracting a bit more. But for this example, I think that using the standard queue for multiprocessing, it's kind of enough well, you will see that it's the performance. It's not super critical here for now. But yes, it's definitely worth to check other alternatives.
Mhm.
Okay, so this loop pygame method, as I said, as soon as you create this process, you pass this loop pygame, which means that after calling the self-process start, this basically means that this function will be start in a separated process in your computer. And basically, you see here that it's kind of having a separated script, right? Where basically here we instantiate the Pygame framework. We create some auxiliary functions, clock to monitor all the different iterations. And here we create the joystick object, as I said. Just for commodity for this example, this joystick object will give us a lot of work done for us. And the interesting part is here that you will see that there is another while true loop, which means that at this point we will start another forever loop. And kind of the way to use a Pygame, you need to get gather all the events by calling Pygame event get. This is something you need so that you can populate values in the joystick instance. And as you can see here, so the way I implement it here, but I just did it for commodity, but it's you can modify very easily this example. So I just decided that in order to move forward and backward the Amiga, I will make use of the left joystick of the Xbox controller. And then in order to turn around the Amiga, basically to send the angular velocities, I will use the right joystick. And you can see here that following this API from Pygame, it's kind of trivial. From the joystick, you just say get axis. The axis one, by brute force, I just figured out that one is left joystick and axis 3 is right joystick. And I'm getting the values here. And as you see, here is where I implement the twist API. So basically, the axis linear is how I create the linear velocity in the X direction. And in that case, we don't have the Y direction, and the angular velocity is the value coming from the second joystick. So once we have these twist methods, that's the methods we want to send to using the Canvas client. I put here in the queue that we set that's going to be used to share the data between processes. So I'm adding the twist command I want to send to the queue. This will put to a queue. And as if you remember, so we have this queue that we are just filling with the twist messages. That basically is the same queue that we are calling here from our main program, the command generator. There is another true that's basically pulling all. So there is a method here, just adding values, commands in the queue. And we have in this generator another loop just taking these commands and sending to the API. So that's kind of the balance here to have different processes. And I think that's more or less it. I don't know, any questions before we show how does it work in reality?
Yeah, I'll just I'll reiterate the passing the generator.
Yeah.
It's the same way we do it in the a virtual joystick or anything where you want to have the bidirectional stream, a generator is in Python is basically treated as an iterable, except it's defined in real time. So this is the yield keyword is basically return, but it'll return multiple times, and in our case, indefinitely. And so because we want to stream messages from this client to the CAN bus service, these twist messages, we use a generator in order to do that, where the messages, each time it basically like steps through, you can almost imagine it as a list of messages where each of the next message that's passed is defined right at the instance that it's to be sent.
Okay, yeah, good.
Cool. Yeah, and this is super cool. I mean, I guess I saw it on Wednesday when we recorded the first time, but on Wednesday it was the first time I'd seen it. It was something Edgar just kind of almost threw together in his free time, and I think it's a really good example of how easy it is to implement things using this Twist API and the CAN bus service.
Yeah. Okay, so I think it's time for the show. Yeah, Ren.
See it.
Gonna show how we move the Amiga. In order to start this program, as I mentioned before, I have created using argparse. These two parameters, host and port, that will be used to create the Canvas client. So this means that the gRPC API that we put, so we enable so that you can specify arbitrary IP addresses and the port where you want to connect. By default, the port of Canvas, it's always 50060. I don't think we're going to change for now, and it should be like a value, fixed value for you. But the host, you see that by default it's local host. This will be the case, for example, that you plug the USB stick in the brain. That will be in host, but since, as explained, so I'm in Barcelona, and what we're going to do is to drive over the internet. What I want to do is to modify the host with the IP of the Amiga that you can see now here in the other part of the screen. So yeah, in order to make that happen, so we use a Tailscale, which basically we are able to connect to all the different robots inside our internal network. But in your case, you should make sure that your computer is at the same network as your robot, so that you can create this internal connection. So here, host, for me, this is the IP of this robot. And another thing you need to do before starting this program is in the dashboard, you need to enable the driving mode to automatic, right? Maybe you can explain a bit that, Kyle.
Yeah, I think I mentioned it earlier, but yeah, on the dashboard, the third tab is the auto tab, at least currently. So that's the tab with the circle and an A in it, and then you click the auto ready button or enable auto, and that'll kick it into auto ready. Once the CAN bus service starts sending commands to the robot that request auto active state, it'll kick into auto active.
Yeah, just to make sure that you are in the correct mode, because otherwise you will feel stuck, like, hey, this is not moving. Okay, so time for show. Okay, so I start my program, my controller. We assume that the dashboard is in the correct state. So now I will start to drive. Reason is Christ. No. Oh, okay. Yeah. So it's kind of funny that I'm driving now. I'm here. I'm just sending. It's amazing because I feel that it's real time. Now I'm turning. Yeah. So it's. I mean, I feel really it's real time. Yes. But also it's funny that like the stream of the camera through the session. I mean, everything feels real time. I don't know how real it is, but okay.
Those are cool.
Yeah,
That's awesome.
nice. Yeah.
Mission accomplished.
I will put it here so that we can see slowly. Yeah. Nice.
Super cool.
I'm just parking the Amiga remotely. That's crazy. Yeah.
That's a good.
Nice.
That's cool. Yeah, and this is something also, since this is this what is it, Amiga Xbox controller repository is open source, so this is something that you can, I mean, you could practically copy and paste it into one of your programs if you wanted to, like, drive the robot around and record data or things like that. You could even, you know, add the canvas client, or sorry, the camera, one of the Oak camera clients to it, maybe trigger like A is take a picture, things like that. So I think this is a super cool example, and I can definitely see applications built on top of this.
Yeah, that's super cool.
Awesome. Well, thanks again, you guys. I think the second one is better than the first one.
Hope so.
All right. Well, I think we'll be back on Wednesday. Do we still have a plan, or is it a secret?
Let's keep it, as a secret.
Yeah.
Okay. Surprise stream on Wednesday.
Yeah.
Don't forget.
Yeah, we'll announce tomorrow.
Okay.
What it'll be, Tuesday.
Cool. Like, comment, subscribe, ask questions in the chat. We'll see you guys in 2 days.
Thank you.
Thank you. Bye.